There is a chess problem in the book, and one person has solved it, and I would be willing to offer a prize for that chess problem to be solved. You have to first find the problem, but then there's this problem. Okay, so what I'd like to do is spend at most an hour, I hope, in discussing the work of Gödel vis-à-vis Russell, and my colleague, Floyd, will take up the main part about the philosophy as it interacts with the philosophy of Russell. So I would say that, well, first of all, that Gödel is the great mathematical logician of the 20th century. He proved the famous Incompleteness Theorem. He established the relative consistency of the Continuum Hypothesis with the construction of L. And Russell is, one might say, the progenitor or the initiator of analytic philosophy per se. There was Frege before, but he was the one to whom everybody would react. He would be the one who would put forward the kind of things that would shape what analytic philosophy would be. And he was the one for whom, against whom you might say, or in reaction to whom Gödel would work in his way, and also Wittgenstein and others. So it's, I think, very nice to be able to put the two together from the beginning at a time, at the earliest part of the 20th century, to see a kind of interaction between the two from the very beginning. It's not always done, particularly about Gödel, and see how things moved one thing to another in his own work. He, of course, had always said that his work was very much motivated by philosophical concerns. And so one sees exactly, or one can lay out, perhaps in this kind of as-if story, or even maybe a just so story, about how it came about that it was so one in coordination with Russell and his own development. One thing I would dispel, not that he's not a genius, but that it was sui generis, that his work actually fits into a kind of pattern which has to do with what one could see in Russell and Principia and so forth, so that one sees a kind of coherence. So it's not a surprise in some way that it is a surprise that he could do that, but it's not a surprise totally, because there's a context in which it arose, the Incompleteness Theorem. Right, so here we are. So Gödel was born, I think, 1906, April 28th, and so he enters the University of Vienna as a strapping young man, so, and I guess, so he is an undergraduate, so to speak, and then he writes his dissertation on the Completeness Theorem, and of course his famous Incompleteness Theorem, and then he becomes a docent, he writes his habilitation, and then he leaves for Princeton soon after 1933. But anyway, the time that he was there, in the first year, so in 1925-26, he attended the seminar Moritz Schlick, studying Russell's 1919 Introduction to Mathematical Philosophy, IMP. That's probably the first time he ever had any exposure to sets, the axiom of choice, ordinals, the transfinite, anything of this sort. And at the very end, actually, is a very interesting chapter that Russell wrote about mathematics and logic. So presumably, he was coming in intending to study physics, and this may have been his first exposure to any sense of what mathematics and logic, how they could be, in some sense, coordinated, or issues that arise within these subjects, and particularly having to do with truth and language. One could say, incidentally, also that IMP was the first book read by Turing when he was an undergraduate at Cambridge. So he got his start there as well, so to speak. It's a chatty book. It's not much detail, but it's a sort of book that's that can be very inspiring for a young man or a young person to see what things there are and what issues there are, not get all the details at first, but to get to the themes at first. Then, after that, he attended the meetings of the famous Wiener Kreis. I suppose that might have been a transmutation of the original seminar there with Schlick and Neurath. And there he came in contact with more philosophical ideas and so forth. In 1928, he purchased a copy of Principia Mathematica, the second edition. The first edition came out about 15 years earlier in the summer. And so at a certain point, perhaps one would say that in his salad days, he was doing all these things and getting exposed to philosophical thinking. Perhaps, but at a certain time, around 1928 or so, one might say that the Wiener Kreis was infected by logical empiricism from his point of view, and so somehow he moved away from that as Wittgenstein's influence became clearer and clearer. So there was a turning, and then he perhaps did not pursue that. Of course, he was doing other things, and he became interested in the completeness problem. Anyway, he purchased this copy, and he read it quite beautifully, I think. He became quite familiar with it. As one could see from his later work, he would quote from the ideas in the terminology and text. Then he took, in 1928 to 29, a course by Rudolf Carnap at the university, the Philosophical Foundations of Arithmetic in the winter semester. The text or synopsis or something from there has been made available in translation and so forth. But it's seen there that, in some sense, there's not much to the content of what he did learn the words like consistency and completeness, but there's not much there in comparison to Carnap's later work that he drew from that course. He would always be opposed to thinking of mathematics as syntax of language, as Carnap would later espouse, but in any case, that text and that course may not have been very inspiring for that as compared to the kinds of things he had achieved and learned through study of Russell. Very quickly, in 1929, he established the Completeness Theorem in the summer. A very famous result that says that, well, maybe either you know it or you don't. That's the law of excluded middle. Anyway, so I'll leave it at that and say that it's a very famous result achieved in his dissertation that's still unpublished then and became published in German later on. And then he established in 1930 the Incompleteness Theorem, much more famous. And of course the two theorems are not contradictory to each other. They talk about different things. So the Incompleteness Theorem is very important for many reasons, and I'll come to its sense and what we did with it, or what people have done with it from that point on. I would say that it's interesting to say first that he worked systematically, that in the summer of, I guess early on in 1930, not in the summer, he came to an understanding that first he was working about, he wanted to talk about the real numbers, but then he realized that there would have to be a reduction of the problem to arithmetic, the natural numbers. Even there was a big problem. And then there he wanted to talk about truth. And truth there was also already a problem, and he saw that he cannot define truth for the natural numbers. So the undefinability of truth for the natural numbers is there, and I'll talk about exactly how it came about, or thought in my Just So story, how it came to that point of view from the Principia. So, and then I suppose somewhere in the next few months he made prodigious progress, so that by the late summer, as he had a conversation with Carnap, he had established the Incompleteness Theorem. So truth is not definable, provability is definable, and you could turn one thing to another and show that there's an incompleteness in arithmetic because of the definability of provability. So first, truth is undefinable, then provability is definable, but then there becomes something called the incompleteness. Okay. I think, yes. Right, so what I'd like to do is step back a little bit and look again at the Principium. So this occurs in 1911 to 1913, the first edition, but he had the second edition, but these two coincide at the beginning. So Russell had a very complex system. He had been confronted with certain paradoxes, Russell's own paradox and various other issues, so that there was something called the vicious circle principle at play. So he wanted to insulate himself in some sense from these things, and so he was the first to actually develop a sense of hierarchy, to move into a type theory. It's the first time anybody ever thought of doing that at all. And so Russell's ramified theory of types is a scheme, I'm just reading from text, of logical definitions based on types and orders, as implicitly indexed by the natural numbers. So the numbers are not explicit, it's just a ranking which is part of the understood notational system. Russell proceeded intentionally. He conceived the scheme as a classification of propositions based on the notion of a propositional function. So a propositional function is, you have some phi, and then, as Frege would say, you need something there, and you fit that in, and it becomes a proposition. So certain parameters would be inserted. So you say something, and then you say something of a number, for example, or of perhaps another proposition, and then it becomes a proposition. So he had a scheme of propositional functions. A notion not really reducible to membership, which we would say is extensional in mathematics, but proceeding somewhat in modern, and I'm afraid not exactly in the right extension of fashion, we may say that the universe is to consist of objects, and not really quite objects, but these propositional functions, stratified into disjoint types. So these are different types, and they're disjoint, with the first type consisting of individuals. So T0 is just individuals, atoms, or elements, or earthings. And each next level is a collection of types of the previous level, and so forth. And the types at the level above the individuals are further ramified into orders. So this is a complex system, one based on the possibility of definability for it. So truth is very important when you want to define things, so you could talk about what things are true. So a notion of truth is always going to be primordial to him, but then with definability, you will be able to capture more and more senses of the primordial. He would be able to get at more and more things in mathematics, especially. Anyway, so the orders O-I-N is a further ramification of the nth level. Okay. And an object is at the ith order in the nth type, is to be defined in terms of individuals or objects in some fixed lower level or lower type. Right? So it's not that complicated if you look at the indexing, and the definitions align for quantifications over that lower order. So you have you have these you have the individuals, and you have all these things, and then you have here all these orders that ramify further this type. But these two, I'm sorry, I guess I got the notation wrong, so it's up here. So that's the nth type. It's ramified into countably many orders. Each order has to do with elements in here and quantification over this, where possibly that m is less than or equal to n, and this j is less than or equal to I when it's out there. So either here you look before you for some place to talk about things and quantify over, or you look down and you capture those things and you define things and put stuff up there. So it's very complicated, and in some sense it almost looks like gibberish if you look at Principia Mathematica, but there is a way to sustain a coherent interpretation of that, looking at that. All right, so This precludes Russell's paradox, a very famous paradox, of course, with which he confronted Frege and other vicious circles, as objects can consist of previous objects, previous not temporally, but in this hierarchy, and are built up through definitions only referring to previous stages. So most of all, he was very much worried about the vicious circle of things defining on themselves and so forth because of the possibility of extensional paradox, or intentional paradox, actually. However, in this system, it's impossible to quantify over all objects in the type Kn, and this makes the formulation of numerous mathematical propositions at best cumbersome and at worst impossible. So Russell was led to introduce this axiom of reducibility, which asserts that for each object there's a predicative object having exactly the same constituents. So it's very complicated, but he, in a sense, is collapsing the orders. Where an object is predicative, it is if its order is the least greater than that of its constituents. So there might be something up there, but you can make it predicative by saying, well, if you were over here, your next thing is going to be actually replaceable by something that's the next one along over here. So you kind of crunch down the definition, so to speak. So he first had the broadest sense of definition, and then he realized that he would have to have this axiom of reducibility for various technical reasons to bring down this thing next to it, sort of sitting next to it over the next level of complication. Right, so he, in effect, reduced consideration to individuals, predicative objects consisting of individuals, predicative objects consisting of predicative objects consisting of individuals, and so on. And that's often called the simple theory of types, which later people like Ramsey would say would suffice for theory of types. So this was a big scheme, and it would be something that Gödel would take in and would stay with him, very importantly, all the way through the relative consistency of the continuum hypothesis. Right, now it's something very interesting, a few pages along, and I think this is, I'll read it in full, and it's, I think, very important, that the words true and false, and he's taking these, he should be taking these in the primordial sense, they're just true or false, have many different meanings. According to the kind of preposition to which they are applied, it's not difficult to see. Actually, this is quite radical because he's going to have different truths for different things all along. But truth, even from the time of his idealistic period, should be just something that's true. It should not be big. It should not be ramifiable, it should not be breakdownable, it should not be something that is relative to anything else. But he's making a very important point here, which has to do with the possibility of expression and definability in language. And so let us take a function, phi of x, and let, this is in its notation, phi of a be one of its values. So there's a provincial function, and you stick parameter a in. Let us call the sort of truth which is applicable to phi of a first truth. So this is the ground level truth, or the truth about things, about individuals, so to speak. This is not to assume that this would be the first truth in another context. It's merely to indicate it is the first truth of the sort we're starting out with. Consider now the proposition for all x, phi of x. If this has truth of the sort appropriate to it, that will mean that every value of phi of x is the truth appropriate to it. It's not clear if it's, again, just whatever truth means for all x. Has, then we say that everything will be phi of x as first truth. Thus we will call that sort of truth that we have appropriate to for all x phi of x second truth. So there's another level of truth for all. We may define the collection of, this thing which has second truth as meaning every value of phi of x has first truth, i.e. for all x, phi of x has first truth. Right? So there's a few things here. He's making this definition, and he's defining, he's weaving into that definition what first truth is inside the language. So he's talking about first truth, and he's talking about second truth, and they're all being built inside the language itself. So he's not stepping out into some meta theory. Truth is being defined internally. And that would be the sort of thing we do in later recursion theory and so forth, that we can define truth at the next level, always in a certain way. But this is the first time it's done, and this is done in 1911. Similarly, if we define there exists x phi of x, the proposition phi x sometimes, i.e., we may less accurately express it, phi x with some value of x, we find that there exists x phi of x. These are intentional predicates for him, so he always has to have a way of paraphrasing. Has second truth if there is an x for which phi of x has first truth. Thus, we may define this thing has second truth as meaning some value of phi of x has first truth, i.e., there exists x, phi of x has first truth. Similar remarks apply to falsehood. Thus, the sort of falsehood that can belong to a general proposition is different from the sort of falsehood that can belong to a particular proposition. So truth itself, though we should be taking this basic, primordial, and inherent in what we are seeking, is now being ramified in some way, and it's being relativized to levels and so forth. And this is done for the very first time in Principia. So set out here is a remarkably early recursive definition. The recursive clause is now familiar as those of the Tarskian definition of satisfiability, but with a crucial difference that with no external vantage point, has second truth and the like are being woven into the language through the very definition that he's making. I welcome any questions if you have any things you want to raise and discuss as I continue. Please raise your hand. I'll be addressing not at the end, but during, if you like. Anyway, so a few pages on, and this is still very early on in the Principia, page 61, and I'm drawing in the elements that are going to be very important in the Gödel undefinability of truth and in the incompleteness theorem. It's all appearing there, and he's interacting with these, and how he moves from one thing to another is going to be the incompleteness theorem. So Richard's paradox is akin to that. So he's going through various contradictions. Actually, there are paradoxes that he's talking about, because he's now worried about certain kinds of linguistic things that are of self-referential sort. And the most famous is the Epimenides, the liar's paradox. But anyway, the Richard paradox is particularly important for the incompleteness theorem. It's akin to that of the least definable ordinal. It is as follows. Consider all decimals that can be defined by means of a finite number of words in English or some fixed natural language. Let E be the class of such decimals. Then E has aleph 0 countably many terms. Hence, its members can be ordered as the first, the second, the third, in some dovetailing fashion. Let M be a number defined as follows. If the nth figure in the nth decimal is P, let the nth figure in N be P plus 1, or circle back from 9 to 0 if in the decimal system, if it's 9. Then N is different from all members of E, since whatever finite value M may have, the nth figure in N is different from the nth figure in the nth of the decimal space composing E, and therefore N is different from the nth decimal. So this number N is different from all the numbers that have been defined, because we have, it's at the nth place, whatever the nth thing is, it's different from the nth item. Nevertheless, we have defined N, we just made this definition in a finite number of words, and therefore N ought to be a member of E. Thus, N is both and is not a member of E. Right? So he's making, again, we are in language, he's making a statement, and it could be in English or something. He's writing this all down, and he just made a finite definition of something, so it should have been inside the list of all possible things you can define in language. Yet it cannot be. So this is a paradox or a problem or contradiction. So now to Gödel. He defined the undefinability of truth for arithmetic in the summer of 1930 as follows. So this is the first thing he does. And you could see in light of the Principia exactly how he might have thought about it this way, or at least this is how one might reconstrue what he had done. Enumerate the formulas in one free variable, and derive a contradiction from the definition, definability of the predication, the nth formula with the nth numeral is true. So you have a propositional function, the nth formula with the nth variable is true. It's exactly the same sort of thing the nth decimal with the nth place. And that's from the Richard paradox. So let me suggest the various mathematical connections, logical connections from Principia. The formula by formula working out of truth. So Russell was the first to do that. Presumption that a general definition is ambiguous. Well, because he has a type theory, he cannot define truth at the top, or he would think he cannot define it. It's precluded because the definition would be outside of his system, because you would have all these levels. You can't define what is true for anything in this level, and that would be understood that it would not be defined. So Gödel would understand that probably you cannot define truth this way. And the operational appeal of Richard's paradox. So you actually have to write down something very carefully, and that's provided by that particular paradox, exactly so. It did not escape Gödel's eye that what Russell called the fundamental question of philosophy, namely the nature of truth, permeated his presentation of types and words. Okay. Now we get to the incompleteness theorem, and it's only a few months later. And there, the central idea of the incompleteness theorem is the formal definability of provability. So to be provable, as we all know, is definable. So to say something is provable means there's a sequence that there's something that proves, and it can be defined in the type theory at exactly these points as we go up. And through what's called the arithmetization of syntax leads to an unprovable formula based on the coded predication. The nth formula in one free variable with the numeral n is provable. So now we have the nth formula with n is now provable. So that can be said, and we get the famous the incompleteness theorem of Gödel. The Principia connections are as follows. Again, you have the Russellian recursion for formulas which is worked out, though not with truth, but with provability, and that can be done. Russell had done the truth within the system, and you could do provability within the system, which thus can be recursively woven into the language. And Richard's paradox is now specifically implemented to transcend definability. According to Gödel's famous incompleteness paper, the analogy of this argument with a Richard antinomy leads to the eye. So provability, truth is up there and cannot really be defined because you look down, but provability is something that can be stated. It can be within the system. So therefore you have an incompleteness according to Richard's paradox. And of course much has been made of how exactly, where you define truth and so forth, provability. Okay, the first move beyond Principia was to make truth versus provability that distinction quite clear. And he did that, and he knew about that as soon as he had given his paper through the early 1930, 31, 32 in seminars. He would make sure, and he even gave a talk in the seminar that this distinction always be made in letters to Carnap and so forth. So he was the very first to really emphasize that difference. Now I want to turn to something very interesting, and that's a prescient footnote. It's footnote 48a, and the little a may suggest a later addition to the incompleteness paper. As will be shown in part 2 of this paper, he never wrote a part 2 of this paper. The true reason for the incompleteness inherent in all formal systems of mathematics is that the formation of ever higher types can be continued into the transfinite. So in the meantime, he had read a paper by Hilbert and he realized that if you put a type up here, as Hilbert would have done and did actually in that paper, while in any formal system at most countably many of them are available, so you could, now if you have an actual indexing, you could actually put a type up there and call it something. And then it can be shown that the undecidable propositions constructed here would become decidable when appropriately higher types are added. For example, the type omega to the system P. So P is the system of for which he proved the incompleteness. And that system was a version of the Principia, so he was basing everything on the Principia. An analogous situation prevails for the axiom system of set theory. So here's the first juncture where he's talking about the truth. If you go to the next type and devise a type there is something there to devise, then at that level you could define truth for this system. But of course, this isn't what Russell would ever have done, because this indexing for Russell was not an explicit indexing. It was simply these things are kind of piled up for him, and he could think about it this way. He doesn't talk about things at an explicit level like this. So these things are there, this type is there, and you could talk about truth over here because you could quantify, as usual, within the Tarski predicate, there is a truth satisfying sequence that does things over here. Right, so the usual Tarski definition can be carried out here for the system here once you go there and talk about arbitrary subsets, if you like, or predications from here. You can predicate the truth up there. Right. So he's thinking about truth. Truth is very important to him, and truth will be something he will seek by going into the transfinite, and he will first start at the omega level. So, and looking back, Hilbert's famous paper was an approach to the continuum hypothesis through transfinite recursion, and while not successful, it led Gödel, who only read the paper in 1930, to entertain transfinite types for getting at higher and higher truth. So each time you have a type, you could go to another level at which you could define truth for that type. So higher types dramatically changed the tenure of Principia, in that types there were only providing a background logical structure, whereas now types were on their way to becoming classes of the system in explicit indexing. So now you have to worry about actually keeping track of these types with actual, what we now would call ordinals, ordinal numbers. Because he wanted to get at the truth at each level, and he realized that you can define truth. Truth here is undefinable within the system, but you can define truth by adding one layer, and then you can define truth for that layer by adding another layer. He gave a very cogent, coherent lecture to the Mathematical Association of America in 1933, and this is the first time, well, one of the first times that something called the Cumulative Hierarchy view of set theory emerged. Also, this view emerged with Zermelo about the same time, well, maybe actually a few years before. So types, he said a few things to change this picture. Types can be cumulative. There's no reason why you can't have Sn. Simply the union, not this, but the union of all the Sn, all these up here. So not disjoint levels, but Sn just accumulating all the n things that came before. So all these will be cumulative. So take this, take a union of these two. For this, take all three, take a union. So accumulate all the types. So that's okay. It doesn't seem to hurt anything. And then it can be, you could go up here and keep doing that and accumulate types over and over again through the transfinite with transfinite indexing. Then he said something very important. When you get up to those infinite types, the first 2 or 3 types already suffice to define very large ordinals. So if you go up to t omega plus 2 or so, parts of the power set, if you like, then you could define well-orderings of all sorts, all the well-orderings of natural numbers and so forth at that level, a few levels up. And then all the ordinals are there, all the ways that you could ever well order any countable set is going to be up there. And then you could grab these definitions and use them themselves to index your system. So if you go up a few types, t omega 2, t omega plus 3, you will be able to define ordinals. You could plug those ordinals and put them into the system, make them explicit, and then you could keep your hierarchy going, and then you could get more and more truth with the indexing that's provided already at those 2 levels. So this stuff will be called some later autonomous progression by Pfefferman and others as they worked on this. For a formal system S based on theory of types, there is an arithmetical proposition unprovable in it, which becomes provable if to S is adjoined the next higher type and the axioms concerning it. So it just says you define truth at that level. He never took Tarski's definition of truth as a tremendous improvement. He thought it was sort of a natural thing to do, actually. So it was not a breakthrough for him, because it was for Gödel endemic to his way of thinking, that you just simply define it this way. You just say truth is defined in this particular way. It's not necessarily some grand thing. It's not a big definition of truth as it might be taken by others. Turning to the justification of the axioms, Gödel finds the situation unsatisfactory, mainly because of the appeal to impredicative definitions. So he said, for it is certainly a vicious circle to generate an object by reference to a totality by which this very object is supposed to be present already. So now he's eliciting certain problems in that lecture about certain kinds of things that are done, especially in mathematics. In mathematics, for example, you might define for a bounded set of real numbers the least upper bound. So that's one of the bounds, and you say it's one of those things that are already there, and you take the least of them. So it's an impredicative, typically impredicative definition. The result of the preceding discussion is that our axioms, if interpreted as meaningful statements, necessarily presuppose a kind of Platonism which cannot satisfy any critical mind and which does not even produce the conviction that they are consistent. So this is actually oft quoted. At this point in 1933, he is very skeptical of a kind of Platonism that's uncritical. However, there is a gradual embrace of Platonism in Gödel's progress, getting at higher and higher truth in steady expansive reaction to Russell. There is first the need for truth to frame unprobability and arithmetic. Then the security of truth in the next higher system, the self-perpetuating need, fueling need for higher and higher systems, and thus the entree into full-blown set theory, with explicit indexing given by ordinals and autonomous progression. This is a step-by-step indispensability argument for Platonism, with more and more objectification becoming indispensable. So he wants to have truth. Each time he wants to have truth, there has to be some kind of thing pushing it. There has to be this kind of embracing of more and more ordinals, for example. With L, he went all the way, actually, indexing, and L is the constructible universe. Gödel established the relative consistency of the axiom of choice in mid-1935, so that's about 5 years from the incompleteness result, and the continuum hypothesis in mid-1937. So there's a long story here which I won't go into, but you need something called the axiom of replacement to show that you can do something by going all the way up. And this axiom of replacement will, as he pointed out, be the analog of Russell's axiom of reducibility. So there's something called the skull and hole argument for establishing the continuum hypothesis, which I won't go into. That's another story. But to establish the continuum hypothesis in the hierarchy that he creates, he says he actually defined something which is the analog, the skull and hole, which is the analog for him in this system of something that Russell would have done with the axiom of reducibility. So the constructible sets are defined to be those sets which can be obtained by, so this is explicit from his first paper, be obtained by Russell's ramified hierarchy of types if extended to include transfinite orders. The extension to the transfinite orders has the consequence that the model satisfies the impredicative axioms of set theory, because an axiom of reducibility can be proved for the sufficiently high orders. So impredicativity by itself raises some skepticism, but the axiom of reducibility will tame it, because something that's defined up there could be defined predicatively, so to speak, earlier. Then in the next paper, in which he describes the proof of the continuum hypothesis, short paper, in modern terms, you have the hierarchy defined as follows. You have the beginning, which is the empty set for him. You don't, in pure set theory, you don't need any individuals. And at each level, you have what we normally call the first order, the collection of things which are definable over the previous level by a first order formula and parameters from that level. And Gödel wrote propositional functions still adhering to the Principia system. And then you go through all the ordinals given before him, and you finish off and close off the universe, and that's the constructible universe. Right. So then he talks about how he proved the continuum hypothesis in L, this hierarchy. And this is what he said. This character of the fundamental theorem is an axiom of reducibility. It's also the reason why the axioms of classical mathematics hold for the model of the constructible sets. For after all, as Russell showed, the axioms of reducibility, infinity, and choice are the only axioms of classical mathematics that do not have a tautological character. To be sure, one must observe that axioms of reducibility appear in different mathematical systems under different names and in different forms. For example, the Zermelo system of set theory is called the axiom of separation. In Hilbert's systems, in the form of recursion axioms. So quite a remarkable, coherent picture that he first sees the axiom of reducibility in Principia, and he carries that theme with him all through, and he sees this particular motif in Zermelo and Hilbert and in his own systems all throughout. Okay, so with my colleague who will take up the cudgels about his work in philosophy per se, I'd like to just mention, having done this work, he turns to Russell's mathematical logic as a subject. In 1944, wrote a paper, and this is his first philosophical publication and his only extended one on somebody else's work, and his first robust statement about his Platonism, which I claim is a kind of indispensability argument. You need more and more, and it's a gradual embrace instead of a sudden embrace of a mitigated sort, making a strong counterpoint in reaction to Russell. So this paper is it's kind of hard to read, and it's also very tentative, but he is laying out certain kinds of things which he will pursue in the Maxwell notebook that she will discuss. So I'll read some of the passages from that paper. So he's gone through this journey from Russell's Principia, the basic themes, and one could see the incompleteness theorem, what's going on through the L hierarchy, all in a coherent picture from the Principia. And the fact that you could hierarchize truth, you could hierarchize their provability, and you could then talk about levels of set theory as you keep going up and up. And finally, the Platonism comes in, so to speak, with the real sense that he gives to the indexing itself of the procedure. You need to have all these ordinals about, and they're real things in some way, to have to climb up with a story that has to go through the axiom of replacement. Anyway, classes and concepts may, however, also be conceived as real objects, namely classes as plurality of things, or as structures consisting of a plurality of things and concepts as the properties and relations of things existing independently of our definitions and constructions. One has to remember that, I mean, there's a lot of talk about Platonism, realism, and so forth. This is quite early on, and he's grappling with something from the beginning of the 19th century, and these are, with Russell, it's sort of a primordial grappling with truth and with what is real and so forth. Of course, there would be a lot of ramifications of these ideas of what is truth and what are real things and so forth. But he's writing down something which for him is a matter of conviction rather early on, having had the mathematical experience of going through these levels through to the consistency of the Continuum Hypothesis. So the second paragraph, it seems to me that the assumption of such objects is quite as legitimate as the assumption of physical bodies, and there's quite as much reason to believe in their existence. They are, at the same sense, necessary to obtain a satisfactory system of mathematics, as physical bodies are necessary for a satisfactory system of our sense perceptions, and in both cases it is impossible to interpret the propositions one wants to assert about these entities as propositions about the data, in the latter case actually occurring sense perceptions. So in some sense, it is his grappling with truth, truth hierarchicalized, that you must believe in him just as much. You must, if you want to take on and accept and understand truth, you have to actually grab it, just like you might have to talk about the physical bodies. It's indispensable. Like you must have electrons, you must have these levels to talk about truth. Or at least ordinals for the indexing to make sense of the hierarchy. Russell had long used data to refer to the starting points, what remain undefined. Data referred not only to sense perception per se, but also to primitive particular concepts. Data, of course, is the word going all the way back, not as it's used now, but data going back to the Greeks. Euclid wrote the elements, but he also wrote a book called Data, about how constructions, one from givens to others, are always carried out. It's about 65 propositions, all data for mathematics or for geometry. Anyway, for Gödel, concepts can be taken to be Russellian propositional functions, construed independently of their combinatorial, linguistic renditions, and that for these there would be intentional paradoxes, like propositions that would be taking on their own senses inside. This only makes it impossible to construct their meaning, which is no objection for one who takes the realistic point of view. Right? And then he noted that primitive predicates and relations such as read or colder must apparently be considered as real objects, and thus neither the basic domain of propositions in terms of which finally everything is to be interpreted, nor the method of interpretation is as clear as in the case of classes. So classes are somewhat more extensional. There are sets or groupings and groupings and groupings, but the concepts read and colder are going to be strewn out along these levels, and there's going to be a sense in which it's going to be hard to get at them. In the second edition of Principia, and that's the first edition, Russell espoused the axiom of reducibility. The second, he tried to do away with the axiom of reducibility. The constructivist attitude is resumed again. The axiom of reducibility is dropped, and it's stated explicitly that all primitive predicates belonging to the lowest type, down here, and that the only purpose of variables of higher orders and types is to make it possible to assert more and more complicated truth functions of atomic propositions, which is only another way of saying that the higher types are only a façon de parler. This statement at the same time informs us of what kind of propositions the basis of the theories to consist, namely the truth functions at the atomic propositions. So if you take what the Russellian constructivistic attitude that Gödel espouses to Russell in the second edition of the Principia, the constructions now become formal definitions. They're not real so much. And what remains is really to talk about what's at the bottom. Because that's where you have to have something in order to, then you construct things after that. Because he has no axiom of reducibility anymore. If, on the other hand, one considers concepts as real objects, the theory of simple types is not very plausible. That's where you have predicate, no more orders, but sort of crunched down, collapsed orders. It's not very plausible, since what one would expect to be a concept, such as transitivity or the number 2, would seem to be something behind all its various realizations in the different levels, and therefore does not exist according to the theory of types. In the Russellian theory of types, there would have to have been a number 2 defined here, and another number 2, and another number 2. At each level, there are two. You have to have the notion of 2 things at here and so forth. So the number 2 as a basic primordial concept would not be able to be expressible in his theory of types. Yet the number 2 is underlying things. It's still a real concept, and that's a problem. Gödel pointed out that to hold that the truths of logic and mathematics are conceptual, reducible to truth about identities and concepts, so maybe in German inhaltlich or contextual, does not eliminate the idea that their axioms have content. If the reduction is effected not in virtue of the definitions of the terms occurring, but in virtue of their meaning, which can never be completely expressed in a formal system of rules. So he's still trying to get at truth in some way, but he realizes that the Russellian constructivist picture cannot get at truth. So he ends, it is reasonable to suspect that it is this incomplete understanding of the foundations which is responsible for the fact that mathematical logic has up to now remained so far behind the high expectations of Peano and others, in accordance with Leibniz's claims, had hoped that it would facilitate theoretical mathematics to the same extent as the decimal system of numbers had facilitated numerical calculations. So around 1600, the decimal system was invigorated by Stephens and so forth, and Newton took it as a great accomplishment and built his algebra of infinite series and so forth. And he had hoped in some perhaps naive way that this would happen if he himself had thought about a theory of concepts in this way. And that it would just happen like that. For how can one expect to solve mathematical problems systematically by mere analysis of the concepts underlying if our analysis so far does not even suffice to set up the axioms. So we don't even know what the axioms there are. But there is no need to give up hope. So that's where he ends, and in some sense this is sort of the direct interaction with Russell through his great mathematical work, and then his latter retrospective reaction to him and his later constructivistic approach, and how unsatisfactory it was for him, and how he would have to find some other way or to build on his own way. And I think that my colleague will now describe how he might have done that, or the speculations he pursued in that direction. Thank you very much.